Swayam Prabha. Digital India. Educated India.
We will take the lead from this characteristic feature of fluids. Fluids cannot resist shear stress under static condition. So, in a static fluid there are no shear stresses. So, now we shortly understand what the total stress tensor means. Okay, let us consider fluids at rest. The total stress tensor for fluids was introduced as shown here, and because total stress tensor is symmetric, I have shown a symmetric total stress tensor here. As we discussed, all the discussions for solids are applicable for fluids as well for total stress tensor. So, what I have shown here is a symmetric total stress tensor. Okay. Now, what did we say? Cannot sustain shear stress. What does it mean? This stress tensor, for if you apply for a fluid at rest under static condition, then you will not have all these shear stress components at all. The diagonal elements are the normal stress components, the off diagonal elements are the shear stress components. Now, we said if you have a fluid under rest, we are considering fluid, let us say a fluid under rest condition, and because there are no shear stresses, all the off diagonal elements become 0, and so the total stress tensor is diagonal for a fluid under static condition, under rest condition. Now, we will find out the stress vector for a fluid under rest condition. We apply the Cauchy's formula. We also seen that the Cauchy's formula is applicable for fluids as well in terms of total stress tensor. The total stress vector is equal to the normal, for our understanding, matrix multiplication with total stress tensor. Okay. So, this is the components of the unit normal vector, and then these are the components of the stress tensor. It is a matrix, only the diagonal components are there. Okay. So, simple matrix multiplication will give us the stress vector, just nx into txx, ny into tyy, similarly nz into tzz. So, the stress vector has been expressed in terms of the components of the total stress tensor and the components of the unit normal vector. Okay. So, we have got an expression for total stress vector in one way. We will now write another expression for total stress vector in another way. Okay. For that, look at the diagram shown here. It is same as what I have seen for solids. You should imagine this as a fluid body, okay, and then a surface in the fluid body. Just to give a feel, I made it colored as blue, but now look at the components. The normal stress is capital Tnn, and the shear stresses are Tns1, Tns2, and then directions S1, S2 are shown here. The stress vector we resolved along the normal and the tangential directions. Now, when we apply this for this applicable for a fluid under moving condition. Now, suppose imagine this to be a surface in a fluid under static condition. What did we say? There are no shear stresses at all. What happens? So, this component is not there, this component is not there. So, what happens? This, remember, this normal direction and the stress vector are at angle to each other because of the presence of shear stress components. Because the stress vector has 3 components, 2 shear stress and 1 normal stress component, it is at an angle to the n vector, normal vector. Now, suppose if these shear stresses are absent, which is the present case, then what will happen? the stress vector will be parallel to the normal vector. There are no shear stress components at all, only one component, and that will be parallel to the n vector. Okay. That is what we are going to state now. Stress vector is parallel to the normal vector, and then when a vector is parallel to another vector, how do we write? The stress vector in this case is parallel to the normal vector, just a scalar multiple of the other vector. So, if a vector is parallel to another vector, we express that as scalar multiple, and that is what we are doing here. The stress vector is some lambda times the unit normal vector. So, your expression for stress vector using the second method becomes lambda nxi, lambda nyj, lambda nzk. I like to summarize this slide again. We made a physical observation based on experimental observation. Experimental observation tells you that in a fluid under static condition there are no shear stresses. Experimental observation is same, that we are used in two different ways. The first implication of the absence of shear stress is that the stress tensor is diagonal. Because of that we got the first expression for stress vector. Once again, going back to the same experimental observation that there are no shear stresses in a static fluid, we infer that the stress vector and normal should be parallel to each other, and hence write the second expression for stress vector. Same physical observation, experimental observation, resulting in two different expressions, two equivalent expressions for stress vector. Both should be same, we will equate it. That is what we are going to see here. That is the first expression. Please note the same experimental observation, same property of fluids. This first equation based on the fact that the stress tensor becomes diagonal. Second, based on the fact that the stress vector becomes parallel to the normal vector. Now, component wise they should be equal to each other, component wise they should be equal. Okay, what does it mean? Lambda nx should be equal to nx txx, nx cancels. So, txx, the normal stress txx acting on of course x plane should be equal to lambda. What about tyy? Tyy should also be equal to lambda. Similarly, tzz should also be equal to lambda. That is what we are going to write now. Comparing the components of the stress vector is same, two different ways of expressing. Okay. Okay, what is the physical equivalence of this statement? If you have a static fluid, first observation is that there are only normal stresses. If there are only normal stresses, okay, if there are only normal stresses, all the normal stresses should be equal to each other. That is a conclusion, and that equal whatever number or scalar we are calling it as lambda. Okay. I will repeat, in a fluid under a static condition there are only normal stresses. If there are only normal stresses, all of them should be same, we are calling it as lambda. Now, in a of course other way of putting it is all diagonal components are equal. So, now our stress tensor becomes diagonal. Earlier we said txx, tyy, tzz. To begin with, let us say we said okay, let them be unequal, but then we have proved that they should be equal, only then equilibrium will be maintained. Okay. Our expression for Cauchy's formula is force balance. So, only if you have only normal stresses, only if all of them are equal, then it will be under equilibrium, force balance will be valid. Okay. That is a other way of interpreting this. Now, the normal stress in a fluid at rest is the pressure, and so Txx is equal to Tyy is equal to Tzz is equal to lambda. Pressure we denote by small p, by small letter p throughout the course, and then this p is the thermodynamic pressure, exactly what I come across in thermodynamics course, no difference at all. We have seen pressure is compressive, and so it is a negative minus P. Okay. So, now what did we say? All the normal stresses are equal. In a fluid under static condition, normal stress is pressure, because pressure is compressive, it is a negative P. Okay. P the thermodynamic pressure, which I come across thermodynamic course. Okay. All the diagonal components are same and they are negative of pressure. So, if you write the total stress tensor in terms of pressure, it becomes minus P in the diagonal, minus P in the diagonal. Now, let us look at the stress element. How do you represent stress element? We have seen a more general representation of stress element. Here the components are only the normal stresses. So, if you want to represent this as stress element, if you take the right hand side face, remember it is a negative P, which means that on a positive phase your force should be along the negative x axis, and then on a negative phase, because it is minus P, your force should be along positive x axis. Okay. Similarly, along y axis, okay, and then similarly along z axis. On all the positive phases, the force should be along the negative axis direction. For example, this is a positive phase and force is along negative direction, and this is a negative phase, force is along positive direction, similarly for z direction. Okay. So, conclusion from this slide is summary of this slide is the stress tensor is diagonal for fluids at rest and the diagonal elements are negative of pressure. Now, let us proceed further, look at one more characteristic. The stress vector was along the normal. So, we represent it as lambda times n vector. This expression we have seen already, multiplying each component with the lambda. Now, let us find out what is the magnitude of the stress vector. What is that? Just square of all the components and then take square root. If you do that, and if you take lambda squared out as common, then you will have sigma nx squared, ny squared, nz squared. It is a unit normal vector that becomes unity and left with lambda, which is minus P. So, the magnitude of the stress vector is the pressure, of course with a negative sign, but what is observation? What is observation? What is that we are saying? Imagine this to be a fluid object, you have a surface in the fluid. What we are saying, the stress under rest condition, what we are saying is that you have a stress vector acting, and then the magnitude of that stress vector is the pressure, of course the negative sign. But what is more important observation is that right hand side does not depend on n, does not depend on the components nx, ny, nz. What does it mean? At the same point I can have a surface like this, I can have a surface like this, whatever be the angle of the surface, the magnitude of the stress vector, the pressure is same and is independent of the orientation of the surface, be it this way, be it this way, be it vertical. So, the pressure acting is same for every plane passing through a given point. Okay. That is what we said, no? N represents the direction of the plane. So, every plane or if you take a plane like this, whatever be the orientation of the plane at the same point, of course imagine a very small plane, the pressure is same. Okay. Now, what is that statement? Pascal's law. At the point pressure is same in all directions, that is what we have stated there. The magnitude of stress vector is the pressure and that is independent of the plane. You have an inclination like this, inclination like this. So, pressure is independent of direction and that is the Pascal's law. Okay. And that is why pressure is a scalar. That is why pressure is a scalar. Why? Of course, we know that any quantity which is independent of direction is a scalar, like density, temperature, etc. Only difficulty is little bit difficult to understand pressure as a scalar. Reason is very simple. Why? That I will explain now. Pressure as force per area, stress vector force per area, stress tensor force per area. So, go by units looks little confusing, but now pressure is a scalar. Why? As we have seen now, we have proved that pressure at a point is independent of direction. Any quantity is independent of direction, only which is can be characterized by magnitude alone is a scalar. That is why pressure is scalar, though the units are force per area. Let us go to stress vector. What did we say stress vector? On a given plane, the plane is specified. So, force acting on a given plane, because the plane is specified and is a force, it is a vector. There is a direction, because the direction of the area is given, you need only the direction of the force, which is the direction of the stress vector, and because you require only one direction, of course magnitude is there, it is a vector. Now go to stress tensor. What does it say? At the same point you can have any number of planes, stress tensor will give you information about stress vector acting on all the planes. So, you are not specifying any plane at all there, that is why it is a stress tensor. So, stress tau is a tensor because it's it has, we said discuss about stress as a stress at a point, it has all the information for forces acting on any plane at that point. So, I am not specifying any direction at all for the plane, that is why you have direction for force, direction for the plane as well, resulting in a stress tensor. This could be tau, or in our case it could be the capital T, total stress tensor also. Just want to illustrate that though the units are same, it could be a scalar as pressure, vector as stress vector, could be a tensor as tau or capital T. Just want to compare the way in which Pascal's law is discussed in fluid mechanics book and then what we have discussed. It may so appear that what we have discussed is different from what in the books, just want to show that both are same. I have taken this picture from this book Sengal. What they show is a wedge shaped element, okay, and they show pressure acting on the faces, okay, and then look at this any surface inclined at an angle, and they show the pressure acting on that face. To begin with, nomenclature P1, P2, P3 etc. is given. This what is this wedge shaped element is nothing but our 2D version of our tetrahedron, because we discussed under 3D condition, we took a tetrahedron. Look at one projection of that and then another plane attached to that. This is a plane at an angle theta with the horizontal. We also said we have a plane at any angle. So, both are equivalent, that is done for 2 dimensional case, we have done a 3 dimensional case. Okay, what are the other differences? Pascal's law is derived in your, let us say, second chapter of fluid mechanics book, and a fluid mechanics book slowly gradually develops fluid under rest condition, then without viscous forces, with viscous forces etc. So, because it is considering fluid under static condition, they do not talk about a general stress, they talk about only pressure as the only normal stress. Because we talked about a general stress, we said more physically fluid under static condition has only pressure as a normal stress. Okay. So, in more specific and then discuss about only pressure, we are more general saying as Txx, Tyy, Tz, but finally of course we also came down to pressure only. Then what they do here is write a force balance in the x direction, here in this case x direction, z direction etc. That is what we also did. What is our Cauchy's law? A force balance in the respective direction, of course. So, both are analogous, ours little more general than what is given there. That is the scope of that chapter. At that level of entry into fluid mechanics book, it is written in a simpler way, but because we are discussing and then taking concepts from solid mechanics, we have a more general discussion. Conceptually both are same. They also finally prove that P1 equal to P2 equal to P1 equal to P2. Similarly, we also proved Tx equal to Ty etc. Finally, they prove that P3 is same. We also proved that the magnitude of stress vector is pressure. So, eventually it is all equivalent to each other. Okay. Okay, now we are in a position to express total stress tensor for fluids. Okay. We have first introduced total stress tensor, and I just made a statement that a fluid under static condition has some stress, when it is flowing it has some additional stress. fluid under static condition, whatever stress it has is what we have discussed now. We have to just add the additional stress. Okay. Total stress tensor has fluid static and fluid dynamic contributions. Now you are in a better position to understand this statement. Okay. Now and then should reduce correctly under static condition. We have two components. So one should vanish when the fluid is not moving and only the static component should remain. Okay. That should be taken into consideration. So the how do we represent the total stress tensor? Let me show the next line also. Okay, the total stress in a moving fluid has two components. One, the component because of the static condition which we call as hydrostatic stress. Other, additional stresses develop because of fluid in motion which are called as viscous stresses. Why viscous stress you will understand later. Right now we will coin a name called viscous stress. Okay. So the total stress in a fluid has two components. Just under static condition it has some stress, we have seen that it is purely due to pressure. That is why I have written as hydrostatic stress, in bracket I have written pressure. Now when it starts moving, additional stresses develop which are the viscous stresses. This tau and the tau in solids are exactly analogous, only this T was different. Okay. That is, now you understand why we introduced capital T when we came to fluids. T has two components, hydrostatic and viscous. This tau in fluids and the tau in solids are analogous. I mean, how is it, you will understand as we go along, but that is why same nomenclature is used, physical significance everything is same, but T has one extra additional component. That is why moment we entered fluids, first line I said let us introduce total stress in fluids. Okay. Okay. So now if you expand the left hand side expressed in terms of the components of total stress tensor, right hand side we have minus P, we have been telling about hydrostatic stress. Remember left hand side let us say tensor or matrix, and the right hand side the viscous stress. Look at this, the components are very familiar to us, but these are viscous stresses in fluids, remember. Okay. These are viscous stresses in fluids, total stress components in fluids. So both of them are 3 by 3 matrix or 3 by 3 expressed in terms of tensor, but now pressure is a scalar. So how do you express? You multiply with the identity matrix. Okay, it is called unit tensor etc., but our language will just say identity matrix or unit matrix. So I multiply this minus P with 1 1 1 along diagonal as my matrix, more formally unit tensor or identity tensor. Okay. And if you sum up term by term, okay, so the off diagonal elements there is no change, only along the diagonal elements. We have seen that under static condition the stress tensor becomes diagonal. So to the diagonal elements minus P gets added. So to just in one line if you want to summarize whatever we discussed now, this stress tensor is analogous to solids, number 1. Number 2, to the diagonal elements minus P gets added. Okay. If you want to just mathematically say, we all discuss the physics very in detail. Bottom line take home point from this is that in slide is that two components, some stress acts when the fluid is under rest, when it flows some additional stresses are there. Okay. Yeah. So now we can understand that highlighted portion. We were here having derived the left hand side of differential linear momentum balance, body force on the right hand side, and then for surface forces on the right hand side we took a diversion to solid mechanics, discussed about the stress vector, stress tensor. Now whatever highlight becomes very clear to you now based on the discussion we had so far. We came to back to fluids, first discussed fluid at rest, and then now look at the term here, it says total stress tensor in terms of pressure and then stress tensor. That is the summary of what I discussed for under fluids. Okay. Now we have to go back to our right hand side of linear momentum balance and complete it. Okay. So just before that, let us summarize what I discussed so far. Total stress tensor was introduced for the case of fluids. Same results of solid mechanics are applicable. Okay. We discussed the difference between solids versus fluids, specifically in terms of response to shear stress. And the most important difference is that no shear stress in a fluid under rest condition, which leads to that total stress tensor is diagonal, also leads to that the stress vector is parallel to the normal vector and only normal stresses are present and they are nothing but the thermodynamic pressure, negative because they are compressive, pressure is compressive. So based on that, we are able to write expression for total stress in fluids. Here we just introduced, okay. Here only we are able to express that. Total stress has two components, hydrostatic stress plus viscous stress, and one stress when the acts when the fluid is in rest condition, additional stresses act when the fluid is flowing.